All right, so occasionally, in the case where we have more than four valence electrons in the number two shell, you're going to have the scenario where you have valence electrons that aren't shared. So this comes up when you get past carbon. Now remember I said with something like nitrogen, nitrogen has 5 valence electrons. So in order to get to 8 in its octet, in order to get to a complete octet, nitrogen only needs to share up with 3 more electrons, and therefore it needs to make 3 more covalent bonds. And what that means is, right, if you're looking at nitrogen, I'm just going to start with nitrogen's Lewis structure. There it is. If I want nitrogen to make 3 bonds and pair up these other 3 electrons, I have a pair of electrons that aren't going to be participating in a covalent bond. So these 3 nitrogens can each participate in a bond, right? And here I'm just making ammonia because I had to make something. Over here I got methylamine. That's a good example as well. But I've left these 2 electrons out. They don't participate in a covalent bond, yet they're part of the octet. They're part of the valence electrons. We call these lone pairs. Now, Lewis structures have to show lone pairs. So if you have lone pairs, you need to show them. And that means that anytime you see a nitrogen, you're going to see at least 1 lone pair, or typically 1 lone pair. Anytime you see an oxygen, you're probably going to have 2. And that's because oxygen in its neutral configuration has 6 valence electrons. And it only needs to pair up 2 of those electrons to have a complete octet. And anytime you see a halogen that is fluorine, chlorine, bromine, or iodine, those group 7 elements, they start with 7 valence electrons. They only need to pair up 1 electron to get a complete octet. So valence electrons you get from the periodic table. That tells you how many electrons are in the neutral configuration. And then you want to get to the octet by pairing up the remaining electrons. So if you have 7, you will need to pair up 1 of them to make 8 total electrons. If you have 6 in the case of oxygen, you need to pair up 2. If you have 5 in the case of nitrogen, you need to pair up 3. But that leaves you with lone pairs, right? So oxygen typically has 2 lone pairs. Chlorine and the halogens in general typically have 3 lone pairs. And those are just pairs of valence electrons that are not participating in covalent bonds. But make sure in your Lewis structures that you show them. All right, so here's a little practice. Normally I would say go take 5 minutes and do these, but I will just show you these. So pause the video right now, go take 5 minutes and do them, and then come back and I will show you how to go ahead and do these. So the way I like to do this is I start by drawing the central atom and going to the periodic table, determining how many valence electrons that atom has, and drawing all the valence electrons around it. So in these cases where we have one atom and multiples of the other atom, the one atom is typically the central atom for the Lewis structure. So in the case of CH4, methane, you've got 1 carbon and 4 hydrogens. The carbon is going to be the central atom. NH3, the nitrogen, will be. OH2, the oxygen, will be. And Cl2, we're going to talk about that in a minute. So carbon had 4 valence electrons. So carbon had 4 valence electrons, so I've drawn them around. Nitrogen had 5, so I've drawn them around. Oxygen had 6, and I got those all from the periodic table, so I've drawn them around. And then I have, for methane, I have 4 hydrogens, each with 1 valence electron. Got that from the periodic table. So I'm going to distribute those hydrogens around with their single electrons, pair up all of those carbon electrons, and make 4 shared pairs of electrons between the carbon and the 4 hydrogens. So same thing with nitrogen. Nitrogen has a lone pair. It only needs 3 bonds to get to an octet. So the 3 bonds are going to be made up by 3 shared pairs with hydrogen. All right, same thing with oxygen. except I only needed to make 2 bonds here. So oxygen has 2 lone pairs and 2 shared pairs of electrons. All right, so Cl2 is a little bit of a different story. If you look at chlorine, chlorine has 7 electrons to begin with. So it only needs to pair up 1 more electron. So I'm going to draw that other chlorine over here with its 7 electrons and say, man, if I could pair up these 2 electrons together, I would satisfy the octets of both of those chlorine atoms. So go ahead and do that. Shared pair between the 2 chlorines and 3 valence pairs on each one of the chlorines. And there you go. All right, so if you can share a pair of electrons in a single covalent bond, you can also do this with multiple pairs of electrons. So if instead of just sharing 1 pair of electrons, we share 2 pairs of electrons, that is 4 total electrons between 2 atoms. Right, here's the case with carbons, where each one of these carbons, I'm sharing 2 pairs of electrons between them, or 4 total electrons. That'll be a double bond, right? That's a double bond. That's just sharing 2 pairs of electrons. You can do the same thing where you share 3 pairs of electrons, so 3 pairs of electrons. Right, and here you can see how the Lewis structures are drawn. You can also draw this Lewis structure, by the way, like that. Nobody really has a problem if you draw that Lewis structure like that. It doesn't matter how you arrange the electrons. Either one of those represents that all 3 of those pairs of electrons are being shared between those 2 carbon atoms, and therefore you have a triple bond. So each shared pair of electrons is a single bond. As you add more shared pairs, you go from single to double, and then from double to triple bonding. All right, so in organic chemistry, drawing Lewis structures gets pretty old pretty quick, and we like to take shortcuts when we're drawing in organic chemistry. We're going to show you a bunch of them as we move through the course, and you're going to see that I draw Lewis structures very rarely. Typically, I draw usually what's called Kekulé structures, and Kekulé structures are no longer Lewis structures. They are representing the bonds as lines. So, you know, if I had H2O and I drew a Lewis structure, it would look like this, where my oxygen has 2 shared pairs of electrons between the oxygen and 2 hydrogens, and 2 lone pairs on the oxygens. A Kekulé structure would look like this. And another way we could draw the Lewis structure is like this. Lewis structures always show lone pairs. Kekulés don't. Kekulés don't show Lewis structure. So this is the Kekulé structure right here. This is a Lewis, and this is a Lewis. The Lewis structures are always showing the lone pairs, and lone pairs are very important. We drop them very quickly, very frequently, and the reason why we drop them is because in more complicated molecules there can be a lot of lone pairs. So sometimes we don't like to draw them if we're trying to move through drawing a structure a bit quickly. The other way that we sometimes will draw compounds is with condensed structures, and these are really an elaborated chemical formula. So if I had water, right, you guys know water is H2O, right? That would be the chemical formula for water, and it would also be the condensed structure for formula. Condensed structures don't show any lines, they don't show lone pairs, they don't show any of that information. They just show the atoms in the relative order that they appear. So you can see up here for something like dimethyl ether, I have 3 hydrogens attached to a carbon, the carbon attached to an oxygen, the oxygen attached to a carbon, and the carbon attached to 3 hydrogens. And the condensed structure looks like this. CH3 representing this. O, CH3. Right? That's a condensed structure, they give you a little bit of structural information. A molecular formula for this would be C2H6O, right? And that just tells you how many of each type of atoms there is in this molecule. The condensed structure shows you a little bit of structural information, right? It shows you that there's a CH3 over on one side, an oxygen in the middle, and a CH3 over on the other side. And that's more information than just C2H6O, right? It gives you a bit more information, but it's not as descriptive as something like the Kekulé structure or the Lewis structure would be. So those are just some ways that we draw things. There are tons of ways that we draw things. I'm going to show you a few more. So these are Kekulé structures of more complex organic molecules. And once you start getting to molecules that have lots and lots and lots of carbons and hydrogens in them, the Kekulé structures even get to be a bit taxing because you have to draw carbon. You have to draw like 18 C's, right? And H's just all over the place, right? So organic chemists are lazy, and what we do is we try to draw things as quickly as possible. And in order to avoid having to draw all of the carbons and the hydrogens, organic chemists have a convention associated with drawing structures. We don't draw carbons. Instead of drawing all of these carbons out, we draw lines. And each end of the line and each vertex, so vertex being the point here, the corner, represents a carbon. So each end of the line and each vertex represents a carbon. So if I were to draw this chain structure that I have up here, right, I would draw it just like this, where each end of the line, there's a carbon, there's a carbon, and each vertex, there, 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 and there, all represent carbons. So ends and bends, right? Ends and bends indicate carbons. And then we drop all the hydrogens. All the hydrogens on carbons, I should say. We drop all the hydrogens on carbons. And here's the reason for that. Carbon usually has 4 bonds. So, and anytime it doesn't, that will be denoted in the structure in some way or another. But carbon usually has 4 bonds. And if you see an end or a bend with less than 4 bonds to it, everything else is hydrogen, up to 4 bonds. So for the reasons we talked about on the previous slide, carbon always has 4 bonds. And here, where I have an end, right, that carbon only has 1 bond drawn. And that means that the remaining 3 bonds to that carbon are all hydrogens. Hydrogen, hydrogen, hydrogen. And they're called implicit hydrogens because they're implied. So we're implying by drawing an end or a bend that any bond up to 4 that isn't drawn in is a hydrogen for carbons. So any carbon that doesn't have all of the bonds drawn in, the remaining bonds are hydrogens. So if I draw this structure up here, it's going to look like that. So we got lots of bends here, right? There's a bend, that's a carbon. There's a bend, that's a carbon. There's a bend, that's a carbon. You get the idea. You go all the way around, every single one of those bends are carbons. And on every one of those bends, right, any bend that's missing 4 bonds, right, that doesn't have a complete 4 bonds, the remaining bonds are made up with hydrogens. So this carbon right here, 3 bonds are shown, 1 going to this carbon. So 1, actually I'm going to label the bonds here. 1 here, 2 here, 3 here. 3 bonds are shown. The 4th has to be a hydrogen. And if you look in the Kekulé structure, there should be a hydrogen there. So it's not drawn, it's implicit, but there's a hydrogen right there. It's implied, right? We're implying that there's a hydrogen there by only drawing 3 bonds to that carbon. So skeletal structures, this is what we're doing right now. These are ends and bends indicate carbons, right? And anything that's missing 4 complete bonds, right? Draw all the other bonds are to hydrogen, and that's assumed. And what that means is we can draw these chemicals very, very rapidly, right? We don't have to worry about drawing all of the electrons. We don't have to worry about drawing all of the carbons, and we don't have to worry mostly about drawing all the hydrogens, because there are a lot of hydrogens in these compounds, and that would take forever.